Every year, around 526 million tons of food, equivalent to 12% of total global production, are lost or wasted due to inadequate refrigeration, temperature monitoring, and storage systems. These figures reveal an important truth. Agriculture does not end in the field. It can only truly survive when supported by transportation. From trucks and trains to refrigerated containers, cargo ships, and airplanes, transportation is the lifeblood of global agriculture. If this system comes to a halt, fruit will rot in orchards, milk will never reach processing plants, food will be unable to cross oceans, and both food prices and the global economy could descend into chaos. So how do agricultural products travel through some of the world's most unusual and essential transportation journeys? Join Terran Works as we explore them in today's video. The history of agricultural transportation began almost alongside the history of agriculture itself. Once humans learned to cultivate crops and raise livestock, they not only needed to produce food, but also had to move grain, meat, milk, fruit, and animals from where they were produced to where they were consumed. At first, agricultural goods were transported by human labor, animal-drawn carts, wooden boats, and river routes. By the 19th century, railways, steamships, and later trucks opened a new era, allowing farm products to travel farther, faster, and in much larger quantities. Today, agricultural transportation has developed into a vast global system. Hundreds of millions of tons of grain are traded across borders every year. In the 2026-27 season alone, global grain trade is projected to exceed 507 million tons. More than 80% of international freight by volume is transported by sea, making cargo ships, containers, and seaports the backbone of agricultural trade. Meanwhile, fresh fruit, milk, meat, fish, and flowers depend heavily on cold storage facilities, refrigerated trucks, reefer containers, and air freight. Transportation is the lifeblood of modern agriculture. It connects farms with processing plants, seaports, supermarkets, and dining tables around the world. In the Val di Non Valley of northern Italy, apples are not transported solely by truck, as they are in many other agricultural regions. After being harvested from orchards along the hillsides, the apples are taken to Melinda's processing facility, one of the best-known apple cooperatives in the Dolomites. There, they are placed in large crates and loaded onto a specialized cableway that carries them down to an underground storage complex. This is not a cable car for tourists, but a transport system designed specifically for agricultural produce. The cableway stretches for about 1.3 kilometers and crosses an elevation difference of roughly 90 meters, moving apple crates from the processing center in Pradaya to storage chambers inside the Rio Maggiore mine. Each hour, the system can carry hundreds of crates, equivalent to around 150 tons of fruit, while potentially eliminating about 5,000 truck journeys every year. What makes the system even more unusual is that the apples are not stored in conventional refrigerated warehouses. Instead, they are placed in underground storage chambers deep inside the mountain. Thanks to naturally stable temperatures, this system helps preserve the fruit for longer, saves valuable land, reduces cooling energy consumption, and limits the number of trucks traveling through the valley. The journey of Italian apples, therefore, does not simply run from orchard to processing plant. It is also a remarkable example of how mountain agriculture can combine with cableway engineering to transport produce more quickly, cleanly, and sustainably. In autumn, as cranberries turn a deep red, farms across the United States and Canada enter the harvest season. Unlike many other fruits, cranberries are not usually picked individually by hand. They grow on low-lying vines in fields known as bogs. Before harvesting begins, farmers flood these fields, transforming them into shallow pools of water. What makes cranberries unique is that they do not actually grow underwater. However, each berry contains tiny air pockets that allow it to float. Once the bog is flooded, harvesting machines move through the field, agitating the water and separating the berries from the vines. Within a short time, millions of bright red cranberries cover the surface, creating a spectacular scene when viewed from above. Workers then use long floating booms to gather the berries into large clusters. Once the cranberries have been concentrated densely enough, pumps or conveyor systems lift them from the water and load them onto trucks. Along the way, the berries may undergo an initial cleaning process to remove leaves, stems, and other debris. The trucks, now filled with cranberries, quickly leave the bog and head to receiving stations or processing plants. There, the fruit is washed, sorted, and turned into juice, cranberry sauce, dried cranberries, and other food products. The transportation journey of cranberries therefore begins directly on the water, one of the most unusual harvesting and handling methods in global agriculture. In Queensland, Australia, transporting sugarcane involves far more than a few trucks leaving the fields. Across the vast cane-growing regions, narrow-gauge trains can be seen moving slowly through the plantations, pulling dozens of small wagons loaded with freshly cut sugarcane. This specialized agricultural railway system was developed almost entirely to serve the annual cane harvest. After harvesting machines cut the stalks into short pieces, the cane is loaded into open wagons known as cane bins. Unlike conventional containers, these wagons have no roofs. They resemble large steel boxes mounted on wheels, allowing the cane to be loaded directly in the fields and hauled straight to the sugar mill. The tracks often run alongside plantations, crossing rural roads, irrigation channels, and small residential areas, creating one of the most distinctive sights of Australia's sugar industry. Importantly, cane trains do not preserve sugarcane through refrigeration or sealed storage. Instead, they move it quickly, continuously, and in large volumes. Once sugarcane is cut, its quality begins to decline, and the sugar content inside the stalks can decrease if processing is delayed for too long. In Queensland, therefore, cane trains are more than just a means of transportation. They are a crucial link that carries sugarcane from the fields to the mills as quickly as possible, before the sweetness within the stalks begins to fade. Bến Tre is a province in Vietnam's Mekong Delta, where coconuts do not leave the farms by truck alone. With a dense network of rivers and canals, many coconuts begin their journey aboard small boats, winding through narrow waterways before reaching collection points, preliminary processing facilities, or factories. This is a transportation method closely associated with Vietnam's Coconut Kingdom. After being harvested, fresh or mature coconuts are gathered into piles along the canal banks. Local people then load them onto wooden boats, motorboats, or larger barges. Fully loaded vessels can travel through narrow canals that trucks cannot easily reach, especially in orchards located deep within river islands or along remote waterways. What makes this supply chain even more remarkable is that nearly every part of the coconut continues on a separate transportation journey. Fresh coconuts are sent to packing facilities for domestic sale or export. Mature coconuts are delivered to factories that produce coconut milk, coconut oil, and desiccated coconut. The husks are transported to facilities that turn them into coir fiber, cocoa peat, mats, ropes, and agricultural growing media. Bến Tre currently has more than 80,000 hectares of coconut plantations and over 163,000 coconut-growing households, with the crop supporting the livelihoods of much of the local population. Coconut products from the province are exported to dozens of countries and generate hundreds of millions of dollars each year. The coconut-laden boats traveling along Bến Tre's rivers are therefore more than a familiar image of life in the Mekong Delta. They represent the first link in an agricultural supply chain that reaches markets around the world. On large export-oriented pineapple plantations, the fruit's journey often begins in the middle of the field on conveyor systems stretching for hundreds of meters. This method is widely used in industrial-scale pineapple growing regions, particularly in Costa Rica, a country that supplies around 70% of globally exported pineapples and ranks among the world's largest pineapple exporters. Once the pineapples reach commercial size and ripeness, workers move along the rows and cut each fruit from the plant with a knife. Instead of carrying individual pineapples weighing around 1 to 3 kilograms over long distances, they place them directly onto mobile conveyor belts running across the field. These systems are often attached to tractors or semi-automated harvesting machines, allowing thousands of pineapples to be moved from the rows to waiting trucks at the edge of the plantation each day. After being loaded onto trucks, the pineapples are transported to packing facilities, where they are washed, trimmed, sorted by size, and inspected for quality. Each fruit may pass through several processing stages before being prepared for the market. From there, boxes of pineapples are loaded onto refrigerated trucks or reefer containers, transported to seaports, and exported to the United States, Europe, and many other markets. Fresh flowers are among the most difficult agricultural products to transport. Unlike grain or coffee, which can remain inside containers for weeks, flowers begin losing moisture, freshness, and value soon after they are cut. Transporting fresh flowers is therefore a race against time, temperature, and humidity. One of the most remarkable examples is the air transport of flowers from Kenya. In growing regions around Lake Naivasha and the Kenyan highlands, roses are cut, cooled, sorted, packed into boxes, and transported directly to Nairobi Airport. Within just 24 to 48 hours, flowers grown in Africa can appear in flower markets and supermarkets across Europe. In the Netherlands, tulips move through a different logistics system. After being harvested from fields or greenhouses, they are chilled, bundled into batches, and transported to major flower auction centers such as Royal Flora Holland. From there, they are loaded onto refrigerated trucks and distributed throughout Europe. During peak season, millions of tulip stems can leave the Netherlands each day, making the country one of the world's largest flower trading and distribution hubs. More recently, a new transportation method has also emerged. Kenyan flowers are being tested for shipment in refrigerated sea containers instead of relying entirely on air freight. The flowers are cooled, transported by rail to the port of Mombasa, and then shipped by sea to Rotterdam. Although this method takes longer, it has the potential to reduce both transportation costs and carbon emissions. Unlike fresh flowers or fruit that depend on an unbroken cold chain, wheat can be transported in enormous quantities across vast distances. After harvesting, the grain is cleaned, dried, and transferred into large storage silos. From there, it begins its journey out of the growing regions by truck, train, or barge. In the United States and Canada, railways play an especially important role. Major wheat-growing regions are often located deep inland, hundreds or even thousands of kilometers from seaports. In the United States, between 2014 and 2019, approximately 50 to 60% of exported wheat was transported to ports by rail. The grain is loaded into specialized hopper cars, forming long freight trains that carry wheat from the plains to export terminals. Alongside rail transport, barges provide another impressive way of moving grain, particularly along the Mississippi River system in the United States. A standard grain barge can carry around 52,500 bushels, equivalent to approximately 1,500 short tons, nearly the same amount as 15 hopper rail cars or 58 large trucks. Thanks to their enormous carrying capacity, trains and barges reduce transportation costs, ease pressure on road networks, and move wheat from remote inland regions to markets around the world. On many export-oriented banana plantations across Latin America, bananas do not begin their journey by truck. Before crossing the ocean in refrigerated containers, many banana bunches first travel through the air on cableway systems running across the plantations. Once the fruit reaches commercial size, the bananas are cut while still green so they can withstand long transportation times. Workers often support the heavy bunches on their shoulders or with protective padding before hanging them onto hooks attached to the cable. The bunches are then pulled in long lines beneath the canopy, moving from the harvesting area to the packing house. The system works like an aerial railway, designed specifically for bananas. It keeps the bunches off the ground, prevents them from being shaken along muddy roads, and reduces scratching, bruising, and damage to the peel, factors that are especially important for export-quality fruit. On large plantations in Ecuador, Costa Rica, and Colombia, cableways also help collect bananas more quickly in regions with heavy rainfall, soft soil, and vast growing areas. At the packing house, the bunches are cut into smaller hands, washed, graded, labeled, and packed into boxes. From there, the boxes are loaded onto refrigerated trucks or reefer containers and transported to seaports for export. The plantation cableway may not carry bananas around the world, but it is the first crucial link that allows them to leave the farm quickly, cleanly, and with as little damage as possible. From Australia's sugarcane trains and banana cableways in Latin American plantations, to coconut boats on the rivers of Beintre and citrus monorails on the hillsides of Japan, every agricultural product follows its own unique journey before reaching consumers. Agricultural transportation is not simply a story of trucks, cargo ships, or refrigerated warehouses. It is the system that keeps food moving, markets connected, and agriculture alive. For centuries, Sargassum was simply a natural part of the Atlantic ecosystem, a floating brown seaweed that acted as a biological oasis in the middle of the ocean. For juvenile fish, sea turtles, and hundreds of other marine species, it was called home. Most of it was concentrated around the Sargasso Sea, a region spanning more than 5 million kilometers in the North Atlantic, nearly half the size of Europe and 3 times larger than the Great Pacific Garbage Patch. But over the past decade, that balance has begun to collapse. Ocean temperatures have risen due to climate change, while millions of tons of fertilizer and agricultural waste have continuously flowed from the Amazon, Congo, and Mississippi rivers into the Atlantic. At the same time, shifting ocean currents have unintentionally created the perfect environment for Sargassum to explode on an unprecedented scale. To this day, Sargassum mass has continued reaching record levels of 37 million tons, forming the Great Atlantic Sargassum Belt, an ocean biomass belt. From NASA spacecraft imagery, many scientists have called it the brown monster of the Atlantic. The worst part is that when decomposing, Sargassum releases hydrogen sulfide, a toxic gas with the smell of rotten eggs that can irritate the lungs and affect the nervous system. Many tourist beaches across Mexico and the Caribbean have been forced to shut down for weeks, causing billions of dollars in losses every year. But the very thing that makes Sargassum a disaster is also what makes it extraordinarily valuable. Because behind the biomass covering the Atlantic lie tens of millions of tons of organic carbon, cellulose, alginate, and marine minerals. And perhaps the most absurd part is this: the biological nightmare spreading across the Atlantic is now gradually becoming a new raw material reserve for post-carbon civilization. Unlike oil or minerals that can be stored for years, Sargassum only truly retains its value while still fresh. After just a few hours under tropical temperatures, this entire biomass rapidly begins decomposing, releasing hydrogen sulfide, losing its cellulose structure, and turning into foul-smelling biological waste. That has pushed the coastal regions of the southern United States, the Caribbean, and Mexico into an entirely new race, collecting millions of tons of seaweed before it has time to rot. At first, most Sargassum was handled directly on beaches using bulldozers, tractors, and mechanized conveyor systems, operating almost around the clock. During the 2018 outbreak alone, the Caribbean spent around $120 million cleaning seaweed from coastlines. Meanwhile, South Florida once estimated cleanup costs could reach up to $40 million annually just to protect tourist beaches. If you were paid around $5 an hour, would you be willing to stand for hours in temperatures above 35 degrees Celsius, shoveling tons of seaweed reeking of hydrogen sulfide and sewage-like odors? But beach collection methods quickly revealed their limits. Bulldozers often removed large amounts of beach sand along with the seaweed, causing coastal erosion and damaging shoreline ecosystems. At the same time, Sargassum landings across the Caribbean were once estimated at nearly 10,000 wet tons per day during peak periods, equivalent to hundreds of biomass trucks. And that was when the battle began shifting out into the open ocean. Humanity actively started hunting ocean waste. This process usually begins with floating barriers stretching hundreds of meters, deployed parallel to coastlines, to block and gather sargassum into massive offshore clusters. Specialized harvesting vessels then move along these biomass corridors, using conveyor belt systems and floating suction pumps to continuously pull seaweed from the ocean surface into onboard storage compartments. Some harvesting vessels operating in Mexico and the Caribbean can now collect between 40 to 100 tons of sargassum per day. Compared to direct beach collection, offshore harvesting allows the biomass to remain fresh, preserving much higher levels of cellulose, alginate, and organic carbon, critical factors for the biomaterials and biofuel industries. But collecting millions of tons of sargassum is only the easiest part of this crisis, because the real challenge lies in figuring out how to unlock the enormous potential of this chaotic biomass and transform it into stable industrial feedstock for large-scale manufacturing. One of the companies leading this race is Sargassum, a Mexican startup attempting to transform millions of tons of sargassum into construction materials for the promising low-carbon economy. Omar de Jesus Vázquez Sánchez started almost from nothing, beginning with small crews collecting seaweed along the coastlines of Mexico. The brick manufacturing process usually begins immediately after the sargassum is transported from coastal collection sites to processing factories. After undergoing initial impurity removal, the seaweed is then further dried down to roughly 15 to 20% moisture content before being shredded into biomass fibers and mixed with clay, lime, biopolymers, or cement, using proprietary formulas to create a biocomposite mixture. This mixture is then fed into high-pressure molds capable of producing nearly 500 bricks per hour, creating construction blocks approximately 3 times lighter than traditional concrete, significantly reducing transportation costs and structural load weight. Thanks to the biological fiber structure that traps air inside the material, homes built with sargassum bricks can reduce indoor temperatures by around 5 to 7 degrees Celsius during summer, while also maintaining more stable heat retention during winter. So far, more than 13 homes for low-income families in Mexico have been built using this material, with each house utilizing nearly 20 tons of recycled sargassum. And that is exactly why the construction industry has begun paying attention to sargassum. The cement industry alone currently emits more than 2.5 billion tons of carbon dioxide every year, while sargassum represents a free biomass source on the scale of tens of millions of tons continuously washing ashore across the Caribbean and North America. But turning sargassum into stable construction material remains a highly complex engineering challenge, as this biomass still carries potential contamination risks and long-term health concerns. And although the future of sargassum in the construction industry remains highly controversial, many companies now see this ocean biomass as a potential solution to the hundreds of millions of tons of petroleum-based plastic gradually engulfing our planet. Every year, the world produces more than 400 million tons of plastic, most of it made from petroleum, and around 11 million tons of that eventually flow into rivers, lakes, and oceans as plastic waste. That is why the ambition of the bioplastics industry is far greater, transforming sargassum into a direct replacement for single-use plastic packaging. Thanks to its natural biofilm forming ability, sargassum, after being desalinated, shredded, and polymer extracted, can be processed into biodegradable films, packaging materials, and food containers capable of naturally decomposing after use. But that is also what creates the greatest challenge. Unlike algae biomass cultivated in stable and expensive controlled environments, sargassum constantly changes its biological composition with the seasons, making polymer refinement far more complex. Yet the ambitions surrounding sargassum still do not stop at biomaterials, because the true gold mine of this ocean biomass lies in its potential to become a nearly limitless energy source for the future. This process usually begins by shredding and drying sargassum before feeding it into anaerobic digestion systems, oxygen-free decomposition systems that use microorganisms to break down the organic compounds inside the biomass. In an oxygen-free environment, millions of microorganisms continuously decompose the seaweed to produce methane and biogas, which can then be used for electricity generation, heating, or further refined into industrial fuel. Remarkably, if around 1 million tons of dry sargassum were processed, the methane produced could theoretically generate enough electricity to power approximately 30,000 to 40,000 households for an entire year. In the Caribbean, Dr. Legina Henry is pursuing an idea once considered absurd, transforming the foul-smelling seaweed covering coastlines into fuel for transportation and future energy systems. Her innovation led to experiments mixing sargassum with wastewater from the rum production industry and blackbelly sheep manure before feeding the mixture into anaerobic digestion systems to generate biomethane. The resulting gas is then further purified to remove carbon dioxide, hydrogen sulfide, and impurities before being compressed at high pressure into bio-CNG, a fuel that can be used directly in natural gas vehicles and industrial power generators. Some early experiments suggest that bio-CNG could reduce fuel costs by nearly half compared to traditional gasoline, while the amount of energy generated from roughly 1 ton of dry biomass would be enough for a natural gas vehicle to travel more than 120 to 150 kilometers. In a more distant future, if something once considered ocean waste can become fuel for transportation, it may also become part of the low-carbon energy systems powering the industries of the future. Beyond fuels and biomaterials, sargassum is now also being explored for the production of textiles, fertilizers, and even livestock feed additives. More remarkably, several companies have recently begun experimenting with turning this ocean biomass into biodegradable paper with lightweight and durable properties, while decomposing faster than many forms of traditional wood pulp paper. And as sargassum begins to be viewed as a strategic biomass resource, the game surrounding the Atlantic is rapidly changing. From Mexico and the Caribbean to the U.S. Gulf Coast, startups and coastal governments are racing to build harvesting fleets, biomass terminals, and industrial supply chains in order to secure control over the enormous marine feedstock continuously appearing across the ocean every year. Because in the future, low-carbon economy, controlling ocean biomass could also mean controlling fuel, biomaterials, and part of the new energy infrastructure of the 21st century. From a biological disaster in the Atlantic, sargassum is now gradually becoming a test of how humanity can transform the climate crisis into the post-carbon economy of the future. So in your opinion, is sargassum truly a new gold mine of the green economy, or simply an overly ambitious experiment by humanity? And while that race unfolds somewhere else in the world, the disappointment of a teenager after his very first scuba dive was igniting the largest ocean cleaning campaign in human history.